Good morning, all of you. That day, we have seen imperfections in solids. We learned point defects. There are three types of point defects. One is stoichiometric defect, then impurity defect, and non-stoichiometric defect. In stoichiometric defect, we have seen vacancy defect and interstitial defect. In vacancy defect, the density decreases. In the case of ionic solids, electrical neutrality is to be maintained, and here again the density decreases. In the case of ionic solids, the vacancy defect is called Schottky defect. Example, the typical example is NaCl. In the case of interstitial defect, the density increases. But in the case of ionic solids, for example, ZNS or AgBr, this interstitial defect is called Frenkel defect. It is also called dislocation defect. In the case of Frenkel defect, the density remains the same. Then we have seen impurity defect. In impurity defect, a foreign ion is coming, replacing the present ions. For example, in the case of NaCl, two Na plus are replaced by one Sr2 plus. So electrical neutrality is maintained in the case of, since it is an ionic solid. So per one per Sr2 plus, there will be one vacancy. So by adding these impurities in this ionic crystal, by adding Sr2 plus in this NaCl, vacancies are created. Next we saw non-stoichiometric defect. Non-stoichiometric defect, that is two types we have seen: metal excess defect and metal deficiency defect. Metal excess defect again are of two categories: metal excess defect due to anionic vacancies and metal excess defect due to extra cations present in the interstitial sites. Metal excess defect due to anionic vacancies, for example, NaCl. NaCl, on passing electricity on or heating, it becomes, it has got, it gets yellow color. This is due to the anionic vacancies. And in this anionic vacancies, electrons are present. So that anionic vacancies or the anionic sites where electrons are present are called F centers or color centers or Farben centers. Due to these color centers, due to this trapped electron, NaCl gets yellow color, KCl gets lilac color, and LiCl gets pink color. So this presence of this electron at anionic site, that is responsible for the color of the crystal on heating or on passing electricity. Next we are going to metal deficiency defect. Metal deficiency defect, for example, FeO or NiO. In these cases, you see the molecular formula in fractional, that is Ni.9801. Normally when we write nickel oxide, NiO, that is Ni1O1. Or normally when we write ferric oxide, that is Fe2O3 or FeO ferrous, FeO. Consider this FeO, that is Fe1O1. In FeO, Fe is in +2 state, O is in -2, that is di-negative, Fe di-positive. For one O, there is one Fe, or if you take 100 O, then there will be 100 Fe2 plus. For 100 O2 minus, there will be 100 Fe2 plus. But when we analyze this FeO crystal, we see deficiency of metal ions. We say metal deficiency defect. Let's see how this occurs. We know that FeO is an ionic crystal. In the case of ionic crystal, electrical neutrality is to be maintained. Electrical neutrality is to be maintained means equal number of positive charges and equal number of negative charges. If there are 100 O2 minus, there should be 100 Fe2 plus. So in that case, electrical neutrality is maintained. But you consider in this way, suppose 3 Fe2 plus means 2 plus, 2 plus, 2 plus. So altogether 6 plus. These 3 Fe2 plus means Fe2 plus, Fe2 plus, Fe2 plus. If they are replaced by 2, 2 Fe3 plus, Fe3 plus, Fe3 plus. 3 Fe2 plus are replaced by 2 Fe3 plus. In that case also, total plus 6 that is maintained. 3 Fe2 plus means plus 2, plus 2, plus 2 means altogether plus 6. 2 Fe3 plus means plus 3, plus 3. That means again plus 6. So my point is, to maintain the electrical neutrality in ionic solids, electrical neutrality is to be maintained. So 3 Fe2 plus can be replaced by 2 Fe3 plus. Now what happens? Gaps are created. Previously there were 3 positions in which these Fe2 plus were present. Now among these 3 positions, only 2 positions are occupied. One by Fe3 plus, another by next Fe3 plus. So vacancies are created. So ultimately what happens? Metal is deficient. Metal is deficient. 3 are replaced by 2. Now the crystal has what? Metal deficiency. Let's see the metal deficiency defect. Fe2 plus O2 minus, Fe2 plus O2 minus, Fe2 plus O2 minus, O2 minus, Fe2 plus O2 minus, Fe2 plus O2 minus, Fe2 plus, Fe2 plus O2 minus, Fe2 plus O2 minus, Fe2 plus O2 minus. Next to plus charge, there should be minus charge. So O2 minus, Fe2 plus O2 minus, Fe2 plus O2 minus, Fe2 plus, Fe2 plus O2 minus, Fe2 plus O2 minus, Fe2 plus O2 minus, O2 minus, Fe2 plus O2 minus, Fe2 plus O2 minus, Fe2 plus. Now, suppose this Fe2 plus and this Fe2 plus and this Fe2 plus. Three Fe2 plus are replaced by, see, Fe2 plus, Fe2 plus, Fe2 plus. So altogether plus 6. These are going to be replaced. So I am going to replace by Fe3 plus, one Fe3 plus, and here one Fe3 plus. Now what happens here? Here it is empty. Electrical neutrality is maintained. Electrical neutrality is maintained. Now gaps are created, interstices or voids are created. Electrical neutrality is maintained, that is required for an ionic crystal. What happens ultimately? The crystal becomes deficient in metal. So we say metal deficiency defect. Metal deficiency defect. So in the case of this FeO, this should be the molecular formula for stoichiometry, but since it is less in Fe, for example, we write this is non-stoichiometric. O1. For 1O, there is no 1 Fe, only 0.93. You can write in this format for easiness. Suppose there are 100 O, there is only 93 Fe. So the crystal is deficient in metal. We call it as metal deficiency defect. Or another example, NiO. NiO means stoichiometric, but if it is Ni 0.98 and O means O1, that means this is metal deficiency defect. If you find like this in decimals, that shows that the crystal is deficient in metal. Even though it is metal deficient, electrical neutrality is to be maintained. So let's see a numerical, how the things are going on. Question. Analysis show that. Analysis shows that nickel oxide has formula Ni 0.9801. What fractions of nickel exist as Ni2 plus and Ni3 plus ions? That means some of this Ni2 plus are replaced by Ni3 plus. 3 Ni2 plus are replaced by 2 Ni3 plus. Now we have to find out what fraction. Fraction means the answer should be less than 1. Maybe 0.6. Then the other fraction will be 0.4. Maybe 0.8. Then the other fraction will be 0.2. Maybe 0.7. Then the other fraction will be 0.3. So all the fractions when you add, it should be equal to unity. So let's see how the calculations are going on. So in this nickel oxide crystal, nickel oxide, it is deficient in nickel. It is deficient in nickel. Electrical neutrality is to be maintained. So for this Ni 0.9801, for the easiness of calculation, I am writing it as Ni 98 and O 100. So in my crystal, I am considering Ni 98 and O 100. And this Ni98 means this contains what all things? Ni2 plus and also Ni3 plus. Ni2 plus and also Ni3 plus. That is understood from the question. Ni means Ni2 plus are there, Ni3 plus are there. And in the case of O, there are 100 O. Each O is minus 2. So we know that the total number of positive charges are equal to the total number of negative charges. Total number of negative charges here, that is 100 into minus 2, that is 100 oxide ions are there. Each oxide ion carries minus 2 charge. So 100 into minus 2, that is minus 200. Negative charges are minus 200. So the total positive charge also should be plus 200. Total positive charges should be plus 200. So you can say that this number, only this number of positive charges are equal to number of negative charges. This number of negative charges is equal to number of positive charges. So number of positive charge is due to what all things? Ni2 plus and Ni3 plus. Ni2 plus ions are there, Ni3 plus ions are there. Their all charges together should be equal to this number of positive charges. So number of positive charges should be 200 because number of negative charges 200. Number of negative charges minus 200 means total charge is minus 200 means number of negative charges 200. 200 negative charges. See, 200 negative charges. So there should be 200 positive charges. 200 positive charges. 200 positive charges are due to Ni2 plus and Ni3 plus. How many Ni2 plus? We don't know. How many Ni3 plus? We don't know. Now, how many Ni2 plus? Let it be X. There are X Ni2 plus. Total number of Ni 98. Among these 98, X are of X Ni2 plus ions are there. So number of Ni3 plus will be 98 minus X. So this total 200, that is due to what all things? X into plus 2, X into plus 2, then 98 minus X into plus 3. Into plus 3. So 2x plus 3 into 98 minus x is equal to this 200. This 200 positive charges are made out of Ni2 plus and Ni3 plus. How many Ni2 plus? X. Suppose x. That means 2x plus 2 into x means 2x. 2x plus 98 minus x into 3, this into 3, which is equal to 200. So I am going to write it again. Our equation comes from what? Number of positive charges is equal to number of negative charges. Number of positive charges should be 200. This 200 is made up of what all things? Plus 2 and plus 3. How many plus 2? How many Ni plus 2? Let it be x. So, 2x plus 98 minus x into 3 is equal to 200. So 2x plus 294 minus 3x is equal to 200, or minus x is equal to minus 94, or x is equal to 94. What is x? X is the number of Ni2 plus ion. X is the number of Ni2 plus ion. So, this is, I am going to write Ni2 plus how many? 94. So, how many Ni3 plus will be there? Ni3 plus, Ni3 plus means that is 98 minus x, that is 98 minus 94, that is 4. There are 4 Ni3 plus and 94 Ni2 plus. So what is a fraction? What is a fraction of Ni2 plus? So Ni2 plus, we have calculated how many? 94 out of this 98. Ni3 plus, how many? That is 4. So what is the fraction of Ni? Fraction of Ni2 plus, that is 94 upon 98. 94 upon 98, that is 0.96. 94, that is 94 upon 98 is equal to 0.96. All right. What is the fraction of Ni3 plus then? Fraction of Ni3 plus, that is 1 minus, that is 1 minus this value, 1 minus 0.96, that is 0.04. 0.04. So this is the fraction of Ni2 plus, and this is the fraction of Ni3 plus. Ni2 plus fraction is 0.96, Ni3 plus fraction is 0.04. Sometimes the question comes in the form in this way, that is calculate the percentage. So to find out the percentage, you can multiply this 0.96 and 0.04 by 100. So percentage of Ni2 plus will be 96% and percentage of Ni3 plus will be 4%. Another question. The composition of a sample of the composition of a sample of Woodside. Woodside is Fe Fe 0.93 O 1.00 means 1. What percentage of iron what percentage of iron is present in the form of Fe3. Fe3 means Fe3 plus. So looking at the formula, we can come to know that, iron is deficient. IRON, iron or iron is deficient. So there are Fe2 plus and Fe3 plus ions. From this formula FeO, O is 2 minus, so Fe is plus 2. Fe is of plus 2. Now what happens? What percentage of iron is present in the form of Fe3 plus? That means in this FeO, not only Fe2 plus, some of the Fe2 plus are replaced by Fe3 plus. Electrical neutrality is maintained. So again you can take in this form, that is Fe93O100 for easy calculation. So here again minus 200 negative charges. So there should be plus 200 positive charges. This positive charge is due to what all things? Fe2 plus and Fe3 plus. So in this positive charges, Fe2 plus and Fe3 plus, both are there. So in the similar way you can calculate, let plus 2 charges are due to this Fe2 plus, so let it be x plus 2x. And what about from plus 3? That is 93 minus x will be of plus 3, which is equal to 200. So 2x plus 93 into 3, 279 minus x minus 3x is equal to 200. So minus x is equal to so what happens? 2 minus 279 that side, so 79. X is equal to 70. Minus x is equal to, that is minus 79. X is equal to 79. So 79 means that accounts for Fe2 plus, right? So what is the percentage, what is the fraction of, or what percentage of iron is in the present of, what percentage of iron is present in the form of Fe3 plus? Now how many Fe3 plus? How many Fe3 plus? X is 79. So how many Fe3 plus? Fe3 plus is equal to 93 minus x. What is 93 minus x? That means 93 minus 79. So here it will be, yes, 14. 93 minus 79, that is 14. So 14 Fe3 plus and 79 Fe2 plus. So let's find out that. I'll be writing Fe2 plus, that is 79. Fe3 plus, Fe3 plus, that is 14. So altogether it is 93. Now what percentage of iron plus 3 1. So percentage of Fe3 plus is equal to, that is 14 divided by total is 93. Total is 93 into 100. So let's calculate that. 14 divided by 93. 93 into 100. So this will be 15%. 15%. So answer is 15%. Thank you. With that, we finish this chapter. In the next chapter, that is solid state, we'll be learning about the concentrations. Next chapter solution. Next chapter solution, we'll be learning the concentration of the solutions and the related things. So thank you. Today we finish this chapter solid state. Next chapter is solutions. Thank you.